Hello. Hello and welcome to this video. So we will continue with the documentation and we had covered till array. So we will move on to weakref. So we will try to finish this in one go. Let's see if we can. It is quite possible, but it may spill up to two videos because I would like to introduce a real world example for this. So we will cover this in two videos, okay? So as you know, this is the exemplified read through. So first I will go through the documentation and at the end I will give you a real world example of this as I have been doing for other modules. So let's get started. The weakref module allows the Python programmer to create weak references to objects. Now, it might be difficult to understand weak references in isolation. But if you are coming from, say, C++ kind of background, where we have shared PTR and you have got cyclic dependencies, or similar thing in Rust, where you want to break the cyclic dependency, you have got the weak PTR, weak pointer. It is similar kind of stuff compared to what Python has, right? It is similar. Weak references are similar to weak pointer in other languages. Now, Python, as you know, is ref counted garbage collection is based on ref counting. And similarly, the write mechanism of C++ or Rust also depends on ref counting. So the concepts are very much similar here. Although it is opaque kind of thing here, you don't see weak references in day-to-day work is because Python does not explicitly use the shared pointer. We don't have that kind of thing. We don't have unique pointer, okay? It is, we don't see shared PTR and unique PTR. And therefore, the presence of weakref is kind of leaves a gap in understanding. So once we are through this module, we will see how weak references can be used. In the following, the term referent means the object which is referred to by a weak reference. A weak reference to an object is not enough to keep the object alive. When the only remaining references to a referent are weak references, garbage collection is free to destroy the referent and use its memory for something else. However, until the object is actually destroyed, the weak reference may return the object even if there are no strong references to it. A primary use for weak references is to implement caches or mappings holding large objects, where it is desired that a large object not be kept alive solely because it appears in a cache or mapping. So read that again and you will see what it means. Notice that it is a primary use. For example, if you have a number of large binary image objects, you may wish to associate a name with each. If you use a Python dictionary to map names to images or images to names, the image object would remain alive just because they appeared as value or key in the dictionary. The weak key dictionary and weak value dictionary classes supplied by the weakref module are an alternative, using weak references to construct mappings that don't keep objects alive solely because they appear in the mapping objects. If, for example, an image object is a value in a weak value dictionary, then when the last remaining references to that image object are the weak references held by weak mappings, garbage collection can reclaim the object, and the corresponding entries in weak mappings are simply deleted. Weak key dictionary and weak value dictionary use weak references in their implementation, setting up callback functions on the weak references that notify the weak dictionaries when a key or value has been reclaimed by garbage collection. Weak set implements the set interface but keeps weak references to its elements just like a weak key dictionary does. Finalize provides a straightforward way to register a cleanup function to be called when an object is garbage collected. This is simpler to use than setting up a callback function on a raw weak reference, since the module automatically ensures that the finalizer remains alive until the object is collected. Most programs should find that using one of these weak container types of finalize is all the need. It is not usually necessary to create your own weak references directly. The low-level machinery is exposed by the weakref module for the benefit of advanced users. Not all objects can be weakly referenced. Objects that support weak references include class instances, functions written in Python but not in C, instance methods, sets, version sets, some file objects, generators, type objects, sockets, arrays, gets, regular expression pattern objects, and code objects. Several built-in types such as list and dict do not directly support weak references but can add support through subclassing. So suppose we have a class dict uh, inherited from dict, and we create an object dict red 1, green 2, blue 3. This object is weak referenceable. See Python implementation details. Other built-in types such as tuple and int do not support weak references even when subclassed. Extension types can easily be made to support weak references. So we'll see weak reference support later on. When slots are defined for a given type, weak reference support is visible unless a weak ref string is also present in the sequence of strings in the slot declaration. We have not yet covered slots documentation, but we will eventually. So first we have the ref function, which takes an object and a callback. Return a weak reference to object. The original object can be retrieved by calling the reference object if the reference is still alive. If the referent is no longer alive, calling the reference object will cause none to be returned. If callback is provided and not none, and the returned weak ref object is still alive, the callback will be called when the object is about to be finalized. The weak reference object will be passed as the only parameter to the callback. The referent will no longer be available. It is allowable for many weak references to be constructed for the same object. Callbacks register for each weak reference will be called from the most recently registered callback to the oldest registered callback. Exceptions raised by the callback will be noted on the standard error output but cannot be propagated. They are handled in exactly the same way as exceptions raised from an object's delete method. Weak references are hashable if the object is hashable. They will maintain their hash value even after the object was deleted. If hash is called the first time only after the object was deleted, the call will raise type error. Weak references support tests for equality but not ordering. If the referents are still alive, two references have the same equality relationship as their reference, regardless of the callback. If either referent has been deleted, the references are equal only if the reference objects are the same objects. This is a subclassable type rather than a factory function. Weak references are generic over the type of the object they reference. Then we have callback. This read-only attribute returns the callback currently associated to the weak ref. If there is no callback or if the referent of the weak ref is no longer alive, then this attribute will have value none. Then we have a proxy function which takes an object and issues a callback optional. Return a proxy to object which uses a weak reference. This supports use of proxy in most contexts instead of requiring the explicit dereferencing used with weak reference objects. The return object will have a type of either proxy type or callable proxy type, depending on whether object is callable. Proxy objects are not hashable regardless of the reference. This avoids a number of problems related to their fundamentally mutable nature and prevents their users as dictionary keys. Callback is the same as the parameter of the same name to the ref function. Accessing an attribute of the proxy object after the referent is garbage collected raises reference error. Then we have get weak ref count of an object. Return the number of weak references and proxies which refer to object. We have get weak refs of an object. Return a list of all weak reference and proxy objects which refer to object. Then we have the class weak key dictionary, which takes a dictionary. Mapping class that references keys weakly. Entries in the dictionary will be discarded when there is no longer a strong reference to the key. This can be used to associate additional data with an object owned by other parts of an application without adding attributes to those objects. This can be especially useful with objects that override attribute accesses. Note that when a key with equal value to an existing key but not equal identity is inserted into the dictionary, it replaces the value but does not replace the existing key. Due to this, when the reference to the original key is deleted, it also deletes the entry in the dictionary. So you see here, we have K1, K2 from the same value of class T. And we create a weak dictionary and we set the key K1 is equal to 1 and K2 is equal to 2. But K1, K2 are same thing here. So when we say K2 is equal to 2, K1 also becomes 2. And if we delete K1, the weak dictionary becomes empty. So the workaround is to remove the key prior to reassignment. So you insert key K1, then you delete, and then you insert K2, and then you delete K1. So K2 will remain here. Weak key dictionary objects have an additional method that exposes the internal references directly. The references are not guaranteed to be live at the time they are viewed, so the result of calling the references needs to be checked before being viewed. This can be used to avoid creating references that will cause the garbage collector to keep the keys around longer than needed. So we have key refs returns an retrieval of the weak key references to the key. We have weak value dictionary mapping class that references values weakly. Entries in the dictionary will be discarded when no strong reference to the values exist anymore. Weak value dictionary objects have an additional method that has the same issue as the weak key dictionary.keyrefs method. Weak value dictionary has a method value refs return an retrieval of the weak references to the values. Then we have weak set class. Set class that keeps weak references to its element. An element will be discarded when no strong references to it exist anymore. Then we have weak method, which takes a method and a callback. A custom ref subclass, which simulates a weak reference to a bound method. That is, a method defined on a class and looked up on an instance. Since a bound method is ephemeral, a standard weak reference cannot keep hold of it. Weak method has special code to recreate the bound method until either the object or the original function dies. Suppose we have a class C, we define a method here, and we have method called. So it takes a self, that is an object. So we create the object of the class C, and then we get a weak ref of this method here. And then we call that weak reference. And then what we do is we create a weak method from C dot method and we call R. So R is bound method C dot method dot main dot whatever script dot C object. And then we call it. So it gets called here. That is method is called. And then we delete C and we invoke garbage collector. And then if we call R, it will be empty. It will not say method call or give the object of this. Then we have callback is the same as the parameter of the same name to the ref function. Then we have finalize function. Return a callable finalizer object which will be called when object is garbage collected. Unlike an ordinary weak reference, a finalizer will always survive until the reference object is collected, greatly simplifying lifecycle management. A finalizer is considered alive when it is called either explicitly or at garbage collection, and after that it is dead. Calling a live finalizer returns the result of evaluating func, and we have argument, key-value argument, and keyword arguments. Whereas calling a dead finalizer returns none. So this is the list and this is the dictionary pair. So that is the generic function of Python. Exceptions raised by finalizer callbacks during garbage collection will be shown on the standard error output, but cannot be propagated. They are handled in the same way as exceptions raised from an object's delete method of a weak references callback. When the program exits, each remaining live finalizer is called unless its at exit attribute has been set to false. They are called in reverse order of creation. A finalizer will never invoke its callback during the later part of the interpreter shutdown when module globals are liable to have been replaced by none. So we have certain functions. All it if self is alive, then mark it as dead and return the result of calling func or then keywords. If self is dead, then return none. Then we have detach. If self is alive, then it dead, mark it as dead and return the tuple object function arguments, tw arguments. If self is dead, then return none. Then we have peak. If self is alive, then return the tuple object function args, tw args. If itself is dead, then return none. Alive property, which is true if finalizer is alive, otherwise false otherwise. At exit, writable Boolean property, which by default is true when the program exits, which calls all remaining live finalizers for which at exit is true. They are called in reverse order of creation. Note, it is important to ensure that func, args, and kwargs do not own any resource references to object, either directly or indirectly, since otherwise object will never be garbage collected. In particular, func should not be a bound method of object. Then we have reference type, the type object for weak referenced objects. We have proxy type, the type object for proxies of objects which are not callable. Then we have callable proxy type, the type object for proxies of callable objects. And we have proxy types, which is a sequence containing all the type objects for proxies. This can make it simpler to test if an object is a proxy without being dependent on knowing both proxy types. You can also see this PEP 205, the proposal and rationale for this feature, including links to earlier implementations and information about similar features in other languages. So it would be interesting to go through this PEP if you're interested. Now we have the weak reference objects. Weak reference objects have no method and no attributes besides ref.callback. A weak reference object allows the reference to be obtained if it still exists by calling it. So we have a class object and we do a pass and we make an object O. Then we create a weak reference object by calling a weak ref.ref O and that is R. Now we say O2 is equal to R. So weak reference object allows the reference to be obtained. So when we call R here, then referent this object is obtained here. Okay. So O is R2. So that is true. If the referent no longer exists, calling the reference objects return none. We delete here O and O2 both. And if we print R here, it will be none. Testing that a weak reference object is still live should be done using the expression ref is not none. Normally, application code that needs to use the reference object should follow this pattern. So we create a weak reference object R here. If O is none, we print object has been reallocated and communicate. Else object is still alive and we use the object. Using a separate test for liveness creates race conditions in threaded applications. Another thread can cause a weak reference to become invalidated before the weak reference is called. The idiom shown above is safe in threaded applications as well as single-threaded applications. Specialized versions of ref objects can be created through subclassing. This is used in the implementation of the weak value dictionary to reduce the memory overhead for each entry in the mapping. This may be most useful to associate additional information with the reference, but could also be used to insert additional processing on calls to retrieve the reference. This example shows how a subclass of ref can be used to store additional information about an object and affect the value that is returned when the referent is accessed. So we have weakref and we subclass from it and we call it extended ref. Now the constructor takes self, some object and callback and kwargs. So what it does is it calls this super constructor with object and callback. Okay, that is, it calls the constructor of this. Now it sets a property counted to 0. And for key value pairs in annotation.items, it sets the attributes of self, key, and value. When it is called, it calls the underscore call of super. And if object is not none, it increases the counter. And OB is equal to OB comma self.counter. Okay, and then it returns the object. right? Now, examples and finalizer objects. We will cover this in the next video along with our practical example. Okay, so we will stop here and we'll continue at example in the next video of Python, which should come possibly on the fourth day. I'll try to maintain the schedule, but there are no guarantees. Okay. Now, I would like to draw your attention to my question answer website, kundika.astrock.org. You can come here and ask and answer Python-based questions. Make use of the Python tag for Python-based question. I will try to answer your questions on Python to the best of my ability, but there are no guarantees. Also, if you are an expert of Python, please join the community and help other members with the knowledge. So I'm trying to build a community which is for programming, and the main objective is to be uh, somewhat lovable community, uh, and we don't want to be as strict as Stack Exchange, okay? Because Stack Exchange is quite strict in terms of what it expects from members. We would be rather flexible related to that. So with this, I will end this video here and I'll see you in the next one. Till then, stay curious, keep learning, and most importantly, enjoy.